Okay, let's start. Okay, so let's start with the model. So what I'm going to do now is I'm going to show you, I'm going to build a very simple model where you can show what the comparative advantage is and where you can make a prediction about trade flows. Okay, the model is very simple. I'm going to here, first of all, state the main assumptions and also state how how the model is robust compared with these assumptions. So why do we need certain assumptions, and why? In some cases we can also do without these assumptions. Okay. So let's start. Okay. So the model I'm going to discuss now builds on the following. So first of all, yes. Okay. First, before starting. Okay. So this is a description of an aggregate economy. Okay, so we are not going to describe here a single elements of the economy, but we are going to describe the economy at an aggregate level. Okay, so something you really should not do in economics, because what you should do is you should describe a single firm, single consumer, and then aggregate. Okay, here we are going to do something kind of different, because we are going to describe the economy from an aggregate point of view. Okay, this is quite old-fashioned. Okay, if you want, but in this case, it's still quite powerful, because even though you are going to describe the economy from a more micro perspective, the main results will be the same. Okay, so you will always have the same drivers. Okay, so it's not that crucial. Okay, for the result. Okay, so what are the assumptions here? So that's why here I'm talking about countries rather than firms. Okay, because then what you have here, the idea is I'm going to describe representative firms, and the idea is you have many of these representative firms that aggregate in a linear way, such that the aggregate description is a good description of what happens indeed. But this might not always be the case. I'm not sure if I'm making sense. Okay, if something's not clear, just let me know. Okay, but here I'm talking about country level rather than firm level. Okay, and I'm going to be more precise about description and hope to clarify things if something's not clear. Okay, here the idea is, so the first idea is that countries have identical constant returns to scale technologies. Okay, so here there are two things in this phrase. There are two things to notice. So first is they have identical technologies. So they have identical technologies. So meaning that firms have access to the same technology. The firms in the two countries have access to the same technology. So why is this? Why do we need this assumption? Because remember, what we would like to do here is we would like to make a prediction about trade flows. So what are we importing? What are we exporting? Okay. Here we assume that the trade flow is not driven by a technology advantage. That is to say that one country has a technology another country has not access to. Okay. Clearly, this would be a straightforward driver of trade. Okay, if one country was technology superior than another, this would be a straightforward driver. Okay, of trade flows. But this is something we would like to exclude, because we would like to model trade flows in a more subtle way. Okay, not in this straightforward, because this is quite clear. Okay, if I have technology you do not have, then I trade with you because I can produce things you cannot. Okay, or I can produce things better than you can do. And this would straightforwardly lead to a comparative advantage. So I would like to exclude this. Okay. It also makes kind of sense, because if we are in an international, kind of sense. I discussed these topics a little bit more in the development economics course, okay? Because clearly you might have that you have technology leaders and technology followers, okay? And then things get a little bit more subtle, okay? But that is to say, you have still developing countries that are quite close to, they're quite close to the technology frontier. So they use similar technologies. Okay? Then you can have clearly developing countries that lag farther behind and could also kind of diverge from the technology frontier. Okay, and clearly in this case, this assumption does not apply. Okay, and clearly we are exporting to developing countries things that incorporate technologies developing countries do not have access to. Okay, this clearly is a straightforward driver. But here I'm going to exclude this. Also because, remember here, what I would like to do is I would like to consider environmental resources, okay? And that's why these technologies are not perhaps the main driver if you consider technology resources in the sense I'm considering here that it means pollution, okay? Okay. So here, clearly, it's something you could discuss, okay, and extend to consider an extension, okay, so if one has a technology advantage as compared to another. But then what you would like to, what you should do in this case is explain why a country is not catching up from a technology point of view, okay, not just assuming that. So explain why a country is not catching up from a technology point of view. So what are the hurdles in adopting technologies that already exist in other countries? Okay, so this is the first part of this sentence. The second part is to see constant returns to scale. Okay, that's going to be crucial as well. So what's the meaning of constant returns to scale? Constant returns to scale means that if you double inputs, you double also output. Okay, this is constant returns to scale. So if you double inputs, you double also output. Okay. So in this case, I'm avoiding two things. I'm avoiding decreasing returns to scale at the aggregate level. And I'm also avoiding increasing returns to scale at the aggregate level. What's the meaning of, so let's see what your guess is. So when do we have at the aggregate level decreasing returns to scale? So what's your hunch? So what's the meaning of having a production function that has decreasing returns to scale? So remember the definition of returns to scale is if there is the simplest thing to think about is double inputs, what happens to your output? If it doubles, then you have constant returns to scale. If it more than doubles, you have increasing returns to scale. If it less than doubles, you have decreasing returns to scale. Okay, this is the definition of returns to scale. Okay. Now, when do we have decreasing returns to scale? Someone has an idea? So what's the meaning of having economically, okay? So from an economic point of view, so what's the intuition of having decreasing returns to scale at the aggregate level? Someone has an idea? Yes, if there is a factor of production that somehow, yes, it's kind of a bottleneck, okay? Somehow reduces the productivity of others, okay? Usually this might be the case if there is land, the land is fixed, okay, in supply. So if you increase production, okay, so you double inputs, what you cannot do is you cannot double land because land is, and usually in fixed supply, okay? And that's why in some cases, okay, when land is a binding or important production factor, okay, you might have decreasing returns to scale. But here, what we are doing is you do not have any of these bottlenecks, okay? So you just double inputs, you double output, okay? Is it clear? Okay, so you don't have any of these restraining, okay, factors of production, okay? Usually what you might have is land, okay? Because land is in fixed supply, okay? We have a finite earth, okay? And you cannot just double, okay, land available, okay? Now, what is the meaning of increasing returns to scale? So when do we have increasing returns to scale?
technology with the same number of factors?
No, that would be a technology improvement. Okay, now here, given the technology, you double inputs, you more than double output. Why might this be the case for the same technology? Was another?
But if you double the inputs, you have more than double of the output.
Yes. Yeah, but the question is why, from an economic point of view, why might this be the case? With the same technology. Yeah, why do we? Yeah, but an example. Okay, so what might happen? So, any ideas? So you have usually increasing returns to scale if, for example, there is a learning effect. Okay, so the technology is the same. Okay, it's not that the technology changes, but you are better at using technology. So usually you have a learning effect. Okay, so you are you're using more and more the same technology, the same tools to produce output, and you're getting better at doing so. Okay, it's like in everything. Okay, so you start producing something, you're not very good. Initially, your costs are high because you are kind of slow in doing things. Then it might also be correct what you said. Okay, by improving over time, you might also improve the technology. Okay, but this is something that, but still, okay, for a given technology, you have increasing returns to scale. Okay, if doubling input, you double output because of, for instance, a learning effect, and this could also lead to improvements in technology. Yeah, you increase efficiency. Yeah, you become more efficient in using the. Now it's clear that in some cases, many cases, okay, you observe in reality increasing returns to scale. Okay, many technologies you have increasing returns to scale. Okay? In the production of things, you have increasing returns to scale. Okay? By the way, other ways to get increasing returns to scale is through agglomeration, okay, agglomeration effects. Okay, so for instance, consider Silicon Valley. Okay, so Silicon Valley, you benefit. So you locate your industry there because you can benefit from others doing similar stuff. Okay, so where do these benefits come from? Well, one major benefit is through the labor market. Okay, so you are a software producer, so it's good to work in an environment where there are other firms that do similar stuff. Because, for instance, if you have to hire a computer scientist, okay, or a software programmer, whatever, okay, they're readily available. And by the way, they can also transfer knowledge, okay, from other firms. Okay, that's why you get benefits, and you produce somewhere where others are already producing. In this way, you can benefit from externalities. Okay? One major one is through the labor market. Okay, that's how you get Silicon Valley and famous agglomeration effects. Okay, so you observe in reality. Okay, is it clear? So that's why this is. These are relevant. We know that these are relevant, but for the moment being, we are excluding this. We are excluding this because this can affect specialization in trade flows in an important way. Okay, because if you start, it's quite intuitive. If you start producing something very early, you might get locked into the production of these things because of a learning effect. So that is to say, you start producing. The famous example is Switzerland with the production of watches. Okay, so Switzerland got a comparative advantage in the production of watches because it started very early, and in this way it gained a comparative advantage because by getting better and better in producing watches, okay, they had very low production costs and had therefore a comparative advantage to others. Okay, that's why it got kind of specialization. Then what one might ask is the specialization a correct one or not? Because it might also be the case that you specialize in the production of the wrong goods. Right? just because of a historical event. So you start producing watches earlier than others. You got better and better and kind of locked in, okay, because you have now very low production costs compared to others, and you continue to do so. But perhaps it might have been better to specialize in the production of other goods, because your real competitive advantage lies in the production of other goods. Because of historical events, you're locked in to the production of this good. Is it clear? I'm making kind of sense. Okay, this is because of increasing returns to scale, because increasing returns to scale means that the more you produce, the better you get, and the lower your production costs are. Okay? Therefore, this can explain, or historically has been used to explain, okay, the specialization of certain countries, okay, the production of certain. But we want to exclude this because this complicates the story kind of, okay, and we want to focus on a more simpler story. Okay, that's why we use constant returns to scale. But the literature has done this, okay, for those of you interested in, not aware of it. Countries have identical tastes. Okay, we assume here the country have identical tastes because, again, this would be a quite straightforward driver of trade flows. Okay, if one country has a different taste than another, clearly then this is a straightforward driver of trade flows. Okay, and again we wanna exclude trivial drivers of trade flows. Then for the moment being, we assume that there are no impediments to trade and no transportation costs, but this is something I'm going to relax later on. Okay, it's not particularly relevant, but for the moment being, I'm going to exclude this. So no impediments to trade, so no trade costs in particular, no frictions, no trade frictions. And in order to keep things as simple as possible, and also this can be extended at least to some, I'm going to consider two factors of production that are available in fixed quantities and a two-country world. And one can think about the two-country case of one being small and the other being large, the other being the rest of the world. Okay, so and in addition to this, and also on this I will comment on, for the moment being, we assume that factors of production are immobile, or they cannot be moved around. But later on, I'm going to remove this. Okay, so you can move around capital as well as labor. Okay, but for the moment being, we assume that capital and labor are fixed. Okay, they cannot. And yeah, for the moment being, I'm considering capital and labor as production as factors of production, and later on, I'm going to extend it to environmental resources. Everything clear? Okay, so now let's go into the details of the, again, for those of you with an economic background will be quite familiar with these assumptions. Others perhaps might not be. Just let me know, okay, if something is not clear. So two goods here assume that there is Y and there is Z. Two factors of, these are the two goods, Y and Z, and two factors of production, labor and capital. And then homothetic production functions. Constant returns to scale production function, okay? With the following properties. Let me perhaps do the following. Let me draw a picture. Okay, let me draw a picture here. So for those of you who are not, and then I'm going perhaps also to draw the. Okay, so just to be clear on this. Okay, I want here a production function has the following well-known standard properties. Okay, so here, if this is my, so this I'm going here to pick just one. Okay, if this is my Y, for instance, and let this be L. Okay, so here I have a production function that looks like the following. So it's a concave. Okay, this would be my F, where I have K0 and L. Okay, so for a given K0, for a given capital level, this is what my production function looks like. Okay, so it has a positive. So the properties are these are the mathematical properties over there. So the first, can you see? Yes, the first derivative is positive. So meaning that by increasing L, you increase output. But my second derivative is negative, okay, meaning that it's concave. So the marginal product of labor, so this is my marginal product of labor is positive, but it's decreasing. Decreasing in L, obviously, okay? So as you increase L, you have always an increasing output, but the increase in output is diminishing as you increase L, okay? Is it clear? I guess this is the same happens also for capital, okay? So also capital has Fk is positive and Fk double K, so the second derivative is negative. Okay. So this is, remember, Fl is the marginal product of labor, Fk the marginal product of capital, and this is positive. So the increase in output given an increase in capital or in labor. And what we also assume is that FLK, which is the cross derivative, is positive. So if you increase capital, then the marginal product of labor increases. Okay. So if you give your workers more tools, okay, then their marginal contribution increases. Okay, this is what it's saying. Okay. Is it clear? Okay, next thing. Let me perhaps this is useful. This is useful for what we're going to see in the second part of the course. So let me perhaps talk briefly about it. Because some of you might not be familiar with it, and it's useful here to explain what I mean with labor intensive or capital intensive. Now here, assume I have here K and L. So what I can depict here is what's called an isoquant. Okay, sorry, this is a brief review of microeconomics. Okay, but I need this in order to be such that everybody is on board. Okay, for what's going on. Follow me. So what is an isoquant? An isoquant is you go to your engineer and ask, I wanna produce a certain amount of certain product. Okay, so to assume I have Q upper bar, and what I want to determine is I want to determine combination of L and K such that this output can be produced. Okay. Now, given the assumptions made above, so the fact that I have the marginal product of labor and capital that are positive and decreasing, I get an isoquant that looks like this here. Okay, this is given for a certain output. Okay, this is my isoquant. Okay, so what does this tell me? Okay, it tells me the following. It tells me that, you see, I can produce output Q. This is my technology, the technology that's available. Okay, I can produce this output Q upper bar not just with one production technique, but with an infinite number of production techniques. And therefore, what I can do is I can substitute L with K. Okay, so I can substitute labor with capital. And what this isoquant tells me is exactly how to substitute labor with capital. Okay? And therefore, the shape of the isoquant tells me the degree of substitutability between capital and labor. And that's going to be a key well, also here it's important, as I'm going to explain in a minute, but it's going to be very important for the second part of the course, okay, where I'm going to discuss more in depth about this issue. Okay, so here, this again is an empirical fact. Okay, so you have to go to your engineer and ask your engineer. Okay, so I have to produce this output. Okay, what are the production possibilities? So, and your engineer that tells you, well, you can use either using these tools and this amount of types of labor, or these tools and this amount, and so on and so forth, if there are any substitution possibilities. Okay, here, for example, okay, so I have production technique A and production technique B. Okay, you see, production technique A uses KA and LA, while production technique B uses LB and KB. Okay, so the outcome is always the same, in the sense that given these inputs, so input would be here LA, KA. Okay, if you use your production function, okay, you get Q upper bar, okay, by definition. And in a similar vein, if you use LB, KB, if you use this in your production function, you get the same output. Okay, because they lie on the same isoquant, but they use their different production techniques. Okay, because you see what is in terms of relative intensity. So what is A compared with technique B? A is more capital intensive. Okay, A is more capital intensive. So A is relatively capital intensive, while B is relatively labor intensive. Okay, technique A is capital intensive, B is labor intensive. Okay. Now, what kind of technique are you going to choose? Well, it depends on costs of production. It depends on costs of production. Because this is, I'm going kind of fast, but I guess many of these things are very familiar. Okay, so if something's not clear, just let me know. Okay, so here you have that F of L and K equals Q. Okay, this is your production. And this implicitly gives you, this defines you the isoquant. Okay, I've depicted here in blue. And it tells you how to switch from one production technique to another. It tells you how to switch from one production technique to another. Let me show you this briefly, okay? If I change here L, okay, if I change L, so suppose there is a small change in L. So by how much do we have to change K such that Q does not change, so production does not change? Okay, so this reads, let me repeat this. So if I change labor, so by how much do I have to change capital in order to still have the same production level? Okay, this I can obtain this from my engineer tells me. Okay, if you want to use fewer workers, how can I substitute workers with machinery? Okay. It's the engineer who tells me what this isoquant looks like. Here, from a mathematical point of view, if we have this production function, I have to look at the production function. Okay, So now you see I can do this by taking the total differential of this here. Okay, if I change L, okay, if I change, so let me do this like this here. If I change L, so what happens? My production changes according to the marginal product of labor. Okay, if I change L, my production changes according to my marginal product of labor, because my marginal product of labor tells me how much my output increases if I increase employment by a small unit. Okay? If I change capital, by how much does output change? It changes according to the marginal product of, oops, sorry, here I forgot that. By dl, okay, this is dq. Now, I'm going to sum everything vertically. I'm going to sum here. And I want therefore here this to be equal to 0 because I want output not to change. And therefore I want FL dl plus FK dk therefore be equal to 0. Now what I have to do is I have just to rearrange things because I want to know how capital has to change if I change labor. And therefore you see this is FL over FK. So this is the ratio of marginal product, labor over marginal product of capital. Okay. What is kind of fast, but I guess it's quite simple. Okay, so what is this? Okay, going back to my isoquant. This is just a refresher, okay, of micro stuff. This is K or L. Now, if this is my, this is here my isoquant given production Q. So what is this? This is known technically as the marginal rate of technical substitution, and it's in a given point. So suppose we are here in E, it is the slope in E of the okay, let me draw this in red. Can you see things? Because I'm not using here slides. Okay, this is my marginal rate of technical substitution. Rate of technical substitution. Marginal rate of technical substitution. Okay, it's the slope of my isoquant in one. Okay. So this is going to be very important for what we're going to see later on. Okay, but still, it's important. Was important here. Okay, is it clear? Because it tells me, okay, if I change slightly, okay, this if I'm here, if I reduce L prime, and this is my dl, it should be very, very small, okay, and this is my K. This should be, therefore, the resulting K prime, and this is my dk. If I connect these two prime, I draw straight lines through E and E prime, and I calculate the slope. It's exactly dk over dl. Then if dl goes to 0, I get exactly the slope in one point. Okay, this is mathematics is known as the limit. Okay, if you take the limit of dl very low to 0, okay, it would be here dk over dl. I hope it's clear. Something is not clear. Okay, so I want this to go to 0. If this goes to 0, then E prime goes close to E. Okay, and in the limit they coincide. Okay, but never exactly the same. I can still draw a straight line through E and E prime and calculate the slope, which is exactly the K over dl, which is my marginal rate of technical substitution. Okay, this is how you can obtain it from an intuitive point of view. Okay. But here, why is this useful? Because if you reduce by dl, remember this in terms of production leads to a loss in production given by FL. By how much do I have to increase K in order to maintain the same production level? Well, it depends on the impact K has on your production, and that's given by Fk. This is how you get FL over of K. If something is not clear, I'm explaining perhaps more carefully what I said before, but perhaps for those of you who are not familiar, it's more confusing. So if something is not clear, let me know. Okay, so no worries. Okay, so something's not clear, just let me know. Okay. I'm aware that for those of you who have never seen this, is kind of wow. For those of you who have already seen this as well, okay. This is just very basic stuff. So that's why let me know if something is not clear, okay? Because I don't want to spend too much things on stuff that you already know. Okay, everything clear? Do not hesitate to stop me, okay, if something's not clear.
What is that? What MRCS stands for?
It stands for marginal rate of technical substitution. Marginal rate of technical substitution. Marginal rate of technical substitution. And it tells you how to substitute labor with capital. And it depends on the technology. Something's not clear, just let me know, because I'm aware of some. I can also explain why I need E prime and how to go from E prime close to E in order to obtain the derivative. Something clear, just let me know, okay? But
you obtain it from the engineers, the marginal rate of that.
yeah, the marginal, I mean, from a practical point of view, you have to ask engineers. This is not an economics problem. Okay, so it's really an engineering problem, because you go to your engineer and tell me, well, I want to produce shoes. How can I produce shoes? Okay, well, you need inputs, you need leather, you need, I don't know, cotton, whatever you want, okay? And then you have to combine them. Well, how can I do this? Well, you can either use machines or you can just use labor, okay? And then the engineer tells you, well, you can use either everything with labor, okay? Or there are these and these machines or these and these tools where you can do without or with less labor, okay? But it's really a technical problem. It's not an economics problem. The economics problem is then, what is the optimal production technique? And I'm going to discuss this now, because then this depends on production costs. But for the moment being, I'm just describing the production technique. It could also be that there is a product that can only be produced using a certain amount of capital and a certain amount of labor, and yet you can't substitute labor with capital. In this case, you have that inputs are perfect complements, okay? But you could also have cases where you can substitute perfectly labor with capital. Okay, there are now production processes where you can do everything completely without labor. Or you can choose to do everything with labor and without machines. Okay, whether to do, I mean, it depends again on the product you're considering, okay? That's an engineering problem. But then, what type of technique to choose is an economics problem. And I'm going to discuss this now. Okay, but for the moment being, I'm just telling you here what the production function looks like, and that's something that the engineer tells me, okay? So how things can be produced. Then, what's the optimal choice? That's an economics problem, and I'm going to discuss this now. Okay, this is clear. So, now, in order to choose the optimal production technique, I need costs, okay? Because what you want to do is, remember, you want to firms here want to maximize profits. And how do you maximize profits? You maximize profits by either maximizing output for a given budget costs, or given an output, you want to minimize production costs. Okay, so let me repeat this. Okay, there are clearly the there's a duality between the two, meaning that they are the same. I mean, there are two faces of the same coin. Okay, so let me repeat this. What you want to do is you have a certain budget. You want to produce with this budget, with this maximum costs. Okay, you want to produce the maximum of output possible, or the other way around. So given a certain output, that you want to produce a certain output, you want to minimize production costs. Okay, and they are the same. I mean, they are the two different sides of the same coin. I'm going to show you just one side. Okay, the other is just. But before doing this, I have to describe what costs are. Okay, what are costs? Production costs in this very simple setting are labor costs and capital costs. In this very simple setting, okay? I have just labor costs and I have capital costs. So labor costs are labor times the wage rate. W would be my wage rate. And R here would be my opportunity cost of capital. Okay, the opportunity cost of capital. Now you see, I can depict this here in my space again. Yeah, sure. Let's use the ruler. Here I have capital and labor. And I can straightforwardly depict this because this is just a very simple function. I can rewrite K equals C over R minus W over RL. Okay, so this is just a straight line. And this would be the ISO cost function. This would be my ISO cost function. And so it's again a straight line. It's a straight line. And let me draw this in. Let's draw this in red. And the slope of this is minus W over R. Okay. So again, here you could have two different production techniques. Okay, suppose I have production technique A and production technique B. Again, they use in a different way capital and labor. Yeah. Okay, but the costs are the same. Okay, the costs are the same because they lie on the same ISO cost function. Okay, this is my cost. Okay. Now what I can do is, now remember, my problem is now given a production level, I want to minimize production costs, or given cost, I want to maximize production. This gives you the optimal production technique. Okay. Now let's do the given production. So suppose given production, minimize costs. Okay. So given production means I have a certain ISO quant here. Okay, let me K and L. Okay, I have a certain ISO quant. Now what I want to do is I want to minimize costs. Okay, so what are costs here? I have a straight line here. So suppose I start with costs like this here. So suppose I start with a production technique like this here. Okay, suppose I start with E0. Okay, is this so? My question is this the so E0? It consists of K0 and L0, and as a consequence, I have C. Oops, does not look like any C. I have C0. Okay. So my question is now: is E0 an optimal choice for production technique? Or put differently, can I do better? Or put differently, can I find another production technique that is less costly? Yes. So what would be a better one? Or what would be the best one?
Point in which the first derivative of the two lines
Are the same, yeah. Yeah, that's put in a very, very complicated way. And here, in a much more simpler way, you would like to have the lowest red line compatible with the production. Okay, but you're right. At the end of the day, the two derivatives have to be the same. But from a practical point of view, you want to reduce. You see, I don't know if you see my ruler. You want to reduce it, the red line, such that it's the lowest one compatible with the production function. But that would be this one here. Let me do this in a dash way. Okay. This is the optimal one. And as you have correctly stated, in this case, what happens is that the derivative of the blue one, which is the marginal rate of technical substitution, in E star, the following happens: the marginal rate of technical substitution in taking in absolute values, because we know that it's negative, okay, is equal to the derivative of the dashed line, which is the relative cost of labor. Okay. So what you have, what this states is that the relative marginal productivity of labor is equal to the relative cost of labor. Okay. So you are paying labor exactly what labor produces in a relative way. Okay. Because this is, remember, this is the marginal product of labor relative compared with the marginal product of capital equals the cost of labor to the cost of capital. Okay, so you're paying, in this point, what you're doing is you're paying labor exactly what labor gives you. While in this case, what you're doing, you see, what's happening in E0. In E0, you can compare again what labor produces compared to what labor costs you. So what happens in E0? Oops, sorry. What happens in A0? What happens in there? You have the, I don't know, can you see the green line? Okay. So the green line, you see the slope of the green line is larger than the slope of the red line. What does it mean from an economic point of view? And from a mathematical point, let me write it down for you from a mathematical point of view, but then let's interpret it. Okay, it tells you that W over R, so the relative cost of labor is larger than the relative marginal product of labor. No, the opposite way around. Okay, sorry, clearly, because the red one is the cost. Okay. Okay, the red one is the cost, and the green one is the marginal product of labor. Okay. With the minus clearly in front. So what does this mean? means that in E0, the benefit, the relative benefit you get from employing an additional worker is lower than, sorry, it's larger than what you are paying the worker. Okay, this tells you always relative compared with capital, actually, because this is from an intuitive point of view, okay? The benefit, the relative benefit you get by employing an additional unit of labor, and this is larger than you're paying this labor unit. That's why you should employ more labor, because benefits are greater than costs. Okay, benefits are greater than costs. Therefore, you should employ more workers. That's why you should employ more workers up to the point where the relative benefits are equal to the benefit to the relative costs. So you should employ more workers till the point where the relative benefits equal the relative costs. Is it clear? So just to be very clear about this picture, then I show you why this is important for our trade story. And later on, this was important because this is going to be important for the second part of the course. Okay, since not everybody perhaps is familiar with this, okay, it's still worth to refresh things. So I can go faster in the second part. Okay. So what's happening? What happens here in the? If we are in E1. In E1, I have L1 and K1. Okay, here you see I have another, I can calculate again the marginal rate of technical substitution. Okay, here, this one. This is my marginal rate of technical substitution. Marginal rate of technical substitution. Here what you have is that the cost of labor compared to capital, okay, is larger than the benefits. Okay, so meaning that you're paying your marginal worker more than what he produces here. Okay, meaning that you should really reduce employment. Yes.
Is relative to capital.
Yeah, it's always to capital. Yeah, because here you substitute labor with capital. Okay, it's always relative. In economics, there doesn't exist. I mean, absolute prices do not exist. Okay? Everything is relative. Okay, so we're never able to get absolute values. We only get relative values. So here we're expressing. So this is a real economy. This is not a monetary economy. In a monetary economy, you express everything in euros. Okay, so you have, I don't know, pen compared with euro. Okay, how to exchange a pen with euro or a pen with dollar. This is a monetary economy. But here we are exchanging goods. Okay, so how to exchange a pen with a paper, okay, or whatever. Okay, but in principle, it's the same. Okay, it doesn't change anything because it's always a relative price. Okay, either pen versus euro or dollar or a pen versus paper. Okay, it's always a relative price. Okay, here we're expressing wage compared with the opportunity cost of capital. Okay, so here you have that the marginal unit of labor costs you more than it produces. Okay, that's why it doesn't pay off to employ this marginal unit of labor. That's why you should reduce employment. Okay, and you do this again up to the optimal point where you have L star and K star. Okay, this is the optimal. This is how you optimally choose your production technique. Okay. Now, everything is clear, kind of fast, but hopefully clear. And now, why is this important for our point? Because now you see, I have now two goods. One is capital intensive, one is labor intensive. What's the meaning of this? The meaning is that if you have running out of time. K and L. Okay, I can share these notes. Okay, later on I share these notes. I post those and on the file online. Okay, where you can download the slides. I have also a folder labeled notes. Okay, which will give me a couple of, day or so. Okay, otherwise just might send me a reminder. Okay, I'll print those in PDF and post the notes. Okay, so if you've got something. If you missed something, do not worry, okay? So given an ISO cost function here, let's draw this in red again. So this is my ISO cost. I have now, so this is C upper bar. Now I have two, I'm not going to describe the other problem. So maximizing output given cost, okay, because it's just a dual problem. It gives you just the same result. Would be just a waste of time. Now I have two products and they have different ISO quants. Okay, the shape is different. So I have one that is like this here, and then I have another one. I don't know if you can see the green one. I guess not. So yeah, you still can. One here. Okay, so you have here, and here the assumption is that Y is capital intensive, so that would be Y. Y would be the blue one. It would be Y. And then this would be here, the green one would be my Z. Z is labor intensive. Okay, and so you see optimal technique choices. I mean that you have here, this would be E Y, and this would be E Z, and therefore this here is K Y L Y. This is L Z, and this is K Z. Okay, so you see that Y is more capital intensive than Z. Okay, is it clear? And this happens for all production levels. Okay, it's not just for one production level. This happens for all production levels. Okay. Questions? Now, the assumption of homostatic production functions are still more technical even. It means that the production techniques remain constant as output changes. Okay, that's straight lines they can here. Yeah, but that's something I'm not using, so I don't want to go into the details. Okay, so it just simplifies results, but I'm not going into that detail. Okay, mathematical detail here. It would just, it's just an additional assumption. So for those of you who are familiar with Cobb-Douglas production functions are the simplest one. Okay, so that satisfy this sum. So you would have something like this. So you would have Y equals K alpha L1 minus alpha. So this is a production function that is homothetic, right? And satisfies all the assumptions I need here. Okay, is it clear? Any questions? Okay, let me just discuss. I'm going to stop 1 minute. Okay, I just want to discuss this figure here. Okay, and I'm going to back to this next week. But then next week I can go, over the solution of the model. Okay, so here, given all these assumptions, okay, what one can do is one can describe what is called the production possibility frontier, and I'm going to characterize it also from a mathematical point of view next week. I'm not going to I don't want to go too much into the mathematical details, but nevertheless, I'm going to show you the main features of this production possibility frontier. Okay? This is important because what I'm going to characterize next week then is the general economic equilibrium. And what this production possibility frontier tells you is what can be produced in an economy, okay, given my technology and given the endowments of factors of production. Okay, so given what my capital stock is, what my labor stock is, and given the technology I have, the production possibility frontier tells me what can be produced in the economy. Okay, I can produce this amount of Z if all factors of production if all endowments are employed in industry Z. I can produce. So let's call this Y upper bar and this Z upper bar if you want. Okay. So I can produce Y upper bar if all endowments are employed in industry Y, okay, and Z upper bar if all endowments are employed in industry Z. Otherwise, I can employ endowments allocate endowments to both of these industries and get this concave production possibility frontier. Okay. For sure, I can also produce zero. Okay, zero is also part of the production possibility set because I can decide to not employ anything and not produce anything. So therefore, everything below this production possibility frontier is feasible, is achievable, given the technology and given my endowments. But clearly what's interesting is the frontier of this set, because it tells me what can be produced if all if all endowments are fully exploited. So all production possibilities are fully exploited. Okay? And the concavity, and I'm going to show you next week why it looks like this. Okay, so what in particular I'm going to calculate. Sorry for this, needed to be done. I'm going to calculate the derivative. Okay, so what the slope of the production possibility is to give you an idea, because I need it in order to solve the problem. But the shape, so the concavity is because of the decreasing marginal product of labor and capital. Okay, that's why I have in both industries. That's why I have the concave shape. Okay. And as you can imagine, also the size of endowment will also affect the size of and the shape of this curve. Okay, that's going to be key, because if I have more labor, or if I have relatively more capital, this is going to change the shape of this. Okay, now because one factor of production is more intensive in one factor or in the other sector. Okay, that's why the endowments are going to affect the shape of this production possibility frontier. Okay, so for the moment being, I don't want to tell you anything more, because then next week I'm going to stop here. But next week I'm going to solve the firm's problem. We are going to see some results we have already seen today. Okay, and therefore makes more sense in view of what we have seen today. But we will see also some additional results that are necessary then to solve the problem. So this is going to be just basic stuff. Okay, so no worries here. It's just a refresher of micro stuff for those of you who have already seen it, not much more. Okay, so here, so sorry again for this introduction, because I know that you have heterogeneous background, so that's why I want everybody to be on board. And then in the second part, this is going to be crucial. So not knowing this, I mean, things are quite more complicated, okay, to understand. Okay, we are not on the same level. Okay, so thanks for the moment being, and enjoy the rest of your week. Okay, bye bye. Thanks.
Thank you.
Thank you. Bye.
Thank you. Bye.